So we have exam 2 coming up. That is, what day is it today? It's a week from today, Thursday, next week. So the day class has it Wednesday night, 3-5, I believe. And the day class has it Thursday, 3-6. So you can come to either one of those that work. And the topics. What? Oh, I know what happened. That's funny. That's never happened before. Because that's my computer. Watch this, though. Wait for it. Okay. Turn it sideways? Well, no, it just does that automatically. Okay. So now, look at that. Okay, so the topics are temperature and kinetic theory, and heat. So none of the stuff we're talking about today is going to be on the exam. Unless you have questions, I'd be happy to answer any questions. No? Huh. You seemed like you were about to ask a question. Huh. Okay. No questions? All right. So last time I just introduced, okay, without looking, what did I just introduce at the end of last time? Heat engines, yep. And the idea of a heat engine is you put heat in and you get work out. And you know, steam engines of different types are heat engines. Combustion engines are sort of a interesting, they're not exactly heat engines, but it's sort of similar in the sense that you use a high temperature to create work. But instead of putting heat in, the cost of that, like in a steam engine, the cost is whatever is increasing the temperature of the gas, you know, the fire, whatever is creating the fire. In a combustion engine, the cost is you have potential energy in the form of a chemical that then blows up and creates this high temperature. But besides that difference, it's sort of the same idea. Okay, and so, without looking again, so here is this is where the work is done. This is connected to the walrus. You have the area over here and the area over here, and they're connected. And if the gas is moving through the cycle this way, does anyone remember what this side of the cylinder is called? This is the boiler, yep. So this is where the heat is input. And does anyone remember what this is called? Yep, condenser. And the condenser, that implies that the gas goes from vapor, a gas, back to a liquid. So it's losing energy there. That's what condense means. So like if it's steam, it comes in as steam and then starts to drip down as water as it cools down over here. So the temperature goes down. There is a valve here and a valve here. So without looking, think about how this is going to work. Think about our goal being to lift up the walrus. When does the valve at A need to be closed, and when does it need to open? If we're trying to lift it, yep. So it's going to open low, close high. Like a good day at the stock market. And B is like a bad day at, B for bad, day at the stock market. This is going to open high, close low. And then there's one more thing going on at C. What's that? What needs to happen at C? Okay, so far, here's what we could have. We could raise the pressure here. It could lift up the walrus one time. It cools down. Now we have low pressure over here, high pressure over here, and that's the end. So we need a pump to make the low pressure gas move into the high pressure area. We have to force it in there. And that takes energy. So some of the energy here is going to be lost to power this pump. And this forces the low pressure gas into the higher pressure region. And so mostly what we're going to talk about is ways to calculate and discuss the efficiency of heat engines. For any heat engine to function, you need a difference in temperature between the boiler and the condenser. And so that makes sense, right? If everything is the same temperature, everything is the same pressure, and if you don't have a pressure difference between here and here, you can't get gas to first flow into the cylinder, and you can't raise the piston. And so no matter how hot you make this, you don't get any movement of the piston unless this is cooler. Okay. And now let's talk about engine efficiency. This is the main thing that we're going to be talking about. Okay, so what is the energy cost of running this heat engine? Forget about the pump for now. Yeah, right. So think of, you can't ever get any energy for free because of conservation of energy. So in order to get energy out, you need to put energy in. The energy we put in is the heat. That's the heat at the boiler, and I'm going to call that QH for the heat. You know, Q is the heat, H for high temperature. And the gain, you know, what you're trying to get out of this heat engine, what's that? Right, so you're trying to get work on the piston. And I'm going to call that W. And let's say lost energy that's of no benefit. So we'd like to minimize this if we could. There are limits to how much we can minimize this, but lost energy of no benefit is heat lost at the condenser. Can anyone think of the everyday name for this? So you have pipes for this coming out of your car. You put bananas in them. Yeah, right. No, I'm not going to fall for no banana in the tailpipe. That's another pop culture reference from before you were born. I'm just trying to make you a well-rounded person. So I'm going to call this QL for the heat at the low temperature. And notice that this is heat added to the gas. This is heat removed from the gas. So if we think of like how these variables would combine to calculate efficiency, it sort of makes sense that you would do it this way. I mean, I think if you were asked to define efficiency, I mean, there's kind of two ways you could think about doing it that would make sense. One would be the work minus QH, and one would be the work divided by QH, right? In some way, it's a comparison of the, you know, how much work you're getting out versus how much heat you're putting into it. We're going to define it as the work. It's the ratio of the work divided by QH. Okay, so if you have a really efficient engine, you get close to as much work out as heat you put in. You can't ever get more. If you have a worthless engine, I mean, if you had a rock and you wanted to try to use that as a heat engine, you'd get no work no matter how much heat you put in, so you'd have zero efficiency. Well, actually, if you did it with a rock, you would get a little bit of work because of thermal expansion. So you'd have to think harder than that to get efficiency of zero, but a rock would be pretty close to zero. So what would be perfect efficiency? What number? Yeah, 1, yep. So E, oh, and yeah, call this lowercase e. So E equals 1, worthless would be, yeah, E equals 0. And so this value can be anything in between those two. And what are the units of efficiency? Well, what are the units of work? Joules. And units of heat? Joules. So they cancel, and it's just a yeah, unitless, dimensionless number. Now we can get another equation by thinking of, so we're going to add heat to the gas in the heat engine at the boiler, right? And that heat can only go, that energy can only go two places. So heat added at the boiler can only be lost from the gas in two ways. It can do work, and so that means positive W, or it can be lost as exhaust. And that is that a positive or a negative QL? That is a positive QL, yep. So the second equation just says QH is equal to the work plus QL. And you can combine these. Let me just sort of, to make reference to these, let's call this one star, this one double star. So you can combine star and double star this way. So we know the efficiency is equal to W over QH, right? That was our definition of efficiency. We can rearrange double star to say that work is equal to QH minus QL. So now combine these two equations and you get that the efficiency is equal to QH minus QL over QH. And so you can rewrite this. Notice we can separate this into two pieces. QH over QH minus QL over QH. Okay, QH over QH is equal to 1. And so another way we can express the efficiency is equal to 1 minus QL over QH. And I guess I'll call that triple star because these three equations are closely related. You saw I just derived the third one from the other two. You can derive any one of star, double star, and triple star from the other two. So in that sense, they're not independent equations. So anything you're going to have to do, you can do with two of these equations. But so there's no such thing as, really there's no such thing as picking the wrong two equations. You can always get there. But in every problem using these equations, there are two of them that are going to make it a lot easier and a different combination that'll take longer. So you just have to, the idea with the kind of problems that you're going to use these for is just getting used to picking the appropriate equation or getting used to doing a lot of algebra. Okay, so let me show you the kind of problem that we'll do with these equations. Any questions so far? So let's say that a heat engine produces work at a rate of 100 horsepower, where 1 horsepower is equal to 746 watts. If the engine's efficiency is known to be 60%, how much power is lost in the exhaust? Okay, so first let's think about the relationship between power and energy, because I gave you all those equations in terms of energy, and these are all given in terms of power. Power, remember, has units of SI units of joules per second, which is equal to watts. And so when we get problems where the units are power, represent power, we can just think of everything as happening. All the numbers they give us are a number of joules that happen in a single second. And then we can do everything in terms of energy just for a second, okay? So this means that if 1 horsepower is 746 watts and the engine is 100 horsepower, that means that the engine is 74,600 watts. And so that means that 74,600 joules are produced each second. And so now we just have to calculate QL each second. And whatever number we get is going to give us the rate of energy loss in the exhaust. Okay, so what do we know? We know that work is equal to 74,600. And we know that QL is what we're trying to find, okay? So we want to find equations that make it easy for us to come up with a relationship between work and QL, okay? So I guess the way that makes sense to me, I mean, we want to take those 3 equations, and only 2 of them, I guess, 2 of those 3 equations, and come up with an expression that only has these 2 variables in it, okay? That's what you need in order to solve for QL, because work is the only one that we know. So I'm going to do it this way. We know one more thing. We know that the efficiency is 0.6. Okay, so I'm going to say that 0.6 is equal to the work over QH. In other words, 0.6 is equal to 74,600 over QH. And now I'm going to use the fact that QH is equal to work plus QL. So if you substitute that in, you get that 0.6 is equal to 74,600 divided by 74,600 plus QL. So 74,600. So I'm going to multiply both sides by the denominator. And then I guess I'm going to do sort of two steps at once and divide both sides by 0.6. So 74,600 plus QL is equal to 74,600 divided by 0.6. I did it a different way before. Can someone divide this for me? Okay. And now subtract 74,600 from both sides, and you get QL is equal to 124,333 minus 74,600, and you get about 49,733 joules. Yeah. Mm-hmm. Okay, so that's the answer, right? No, because this is an amount of energy, and I asked for a rate of energy loss. So remember that what we were calculating is the energy loss per second. So the rate of energy loss is 49,733 watts. Any questions about that? Okay, so it's just manipulating those three equations. It's going to take practicing a couple times, but it's these kind of problems are really just algebra problems, and just remembering what the sign convention means for each one of these variables. All right. So now we'll find out a little bit more about the maximum possible efficiency. So we can be more specific about maximum efficiency of a heat engine if we know the temperature of the boiler and the temperature of the condenser. Without knowing that, like if we don't know those temperatures, all we can say is that the efficiency has to be less than 1. I guess less than or equal to 1. Okay, but we can actually, that's not a very helpful relationship because efficiencies tend to be much lower than that. So it's helpful to be able to pin it down more than that. And with these temperatures, we can calculate the ideal efficiency I'll call that lowercase e ideal. And this ideal efficiency is the efficiency of this theoretical type of heat engine, theoretical. Called the Carnot engine. Carnot is just the name of another guy. And this E ideal is equal to 1 minus TL over TH. TH, sorry. So this is helpful, but this equation is something that trips a lot of people up. So be careful on this. Notice that the equation for E ideal looks a lot like equation triple star from before. Equation triple star said that a specific engine's efficiency is equal to 1 minus QL over QH. This one says the ideal efficiency, like the actual engine will have an efficiency lower than this, but the absolute theoretical maximum of that engine would, operating at those temperatures, is 1 minus the temperature at the condenser divided by the temperature over the boiler. And the reason, so this is confusing because it's the same form, 1 minus something over something. And even 1 minus something at the condenser divided by something at the boiler. And even more than that, it's really easy to confuse heats and temperatures because in everyday speech, we tend to think of heat as like a temperature. So you got to be careful when you use these two. Equation triple star and this, they're measuring different things. You need to be sure that you understand the difference between E ideal and the actual E of some specific engine. And you need to make sure that you're making the distinction between those temperatures and those heats. So let me do, no, I don't, I guess I'm doing a problem related to this in a little bit. Any questions about that right now? Okay. The last thing I have to talk about, and then I'm just going to go through a few example problems. So this is the last thing in the thermodynamics section, is entropy. And entropy is related to the second law of thermodynamics. Um, so you can think of entropy as essentially a measure of energy disorder. For a given amount of energy, of thermal energy, entropy is low if all that energy is concentrated let's say concentrated in one place, creating a very hot spot and a very cold spot. Entropy is high for that amount of thermal energy. If all the energy is spread out evenly, so everything is the same temperature. Okay, so you can make up all sorts of things to measure. I mean, you could define a quantity called the Bolton that had measured the length of something times its shininess divided by its energy, whatever. Like, so someone came up with this idea of entropy, but why does it matter? Like, what's the useful distinction to be made between low entropy and high entropy? So think of it in terms of heat engines, the stuff we've just been talking about. For a given amount of energy, something with low entropy is very useful for building a heat engine. Okay, it's very useful for getting work out of it, because the high temperature region can be the boiler, the low temperature region can be the condenser, and you can use that to generate useful energy. Okay. On the other hand, if the entropy is high and everything's the same temperature, in order to make a heat engine do anything, you need a temperature difference between the hot spot and the cold spot. So even though these two things could have the same amount of energy, I mean, remember that we calculated early on, there's this big amount of thermal energy just sitting here in the air, right? All that amount of energy could be represented in very different ways. You could have a very hot spot and a very cold spot that had the same amount of total energy as this air, or you could have this air just sitting here all one temperature. Well, the hot spot and the cold spot you'd be able to use to get work. The air sitting here, we can't use unless we take it to somewhere else that has either a much higher temperature or a much lower temperature. Okay. So low entropy is useful because it can be used to produce work. Think of it as being the boiler and the condenser of a heat engine. High entropy means the energy is not useful. So it can't be used to produce work. Okay, so McDonald's hamburgers, you know, whatever, they all taste the same. But if you wanted to, if you weren't going to eat it, but you were going to try to use it as a heat engine, assume that they all had the same amount of energy. What is, so you guys remember this one? Kaylee doesn't. Okay, so this is called the McDLT. Remember this? You had the vegetable stuff over here. You had the hamburger over here. Versus here's a Big Mac. Yeah, sorry. That wasn't realistic. So assume that these each have the same amount of thermal energy. Which is high and which is low entropy? The Big Mac is high entropy. What we want to make a heat engine is low entropy. Okay, the entropy is a measure of how difficult it is to use it as a heat engine. The Big Mac, everything's hot, everything's the same temperature, you know. So you can't take half of it and use it as a condenser, a boiler, and half of it and use it as a condenser. It's not useful that way. The McDLT, what?
Well, technically the Big Mac is less entropic.
Right, isn't it?
I mean, by the analogy you're using, I mean, they're separate, so there's a bigger difference, but the Big Mac is less entropic because it's less random.
Well,
Just by standard.
no, this one, so this has a cold side and a hot side. And if these have, say this is all warm, so that it has the same total energy. This, you could hook up a piston in between. And you could lift one time a very small walrus. Because of the temperature difference. So that's low entropy. This one, everything's the same. You can't get any work out of it. So this is high disorder, high entropy. the I think that's an okay way to think about it. Yeah, I mean, I don't think that's totally necessarily true, but that's kind of the right thinking, I think. Yeah. So MIC-DLT has low entropy, which means good usefulness. The Big Mac has high entropy, not useful for work. And now for calculating entropy, for a constant temperature system, the change in the system's entropy is equal to Q over T. So change in S is the change in the system entropy. Q is heat added to the system. And T is the temperature of the system. Okay, so let's think about how this works. Like, in a way, entropy is a measure of how easy it is to use. So when a system has energy added to it, the question is, how easy is it going to be to use that added energy to produce work? Okay. You get a big change in entropy if you put energy into something, and it's going to be really hard to ever use that energy again. So if you think of energy, how could energy be useful to produce work? Well, you have to then, to use that energy as work, that energy has to be in the boiler of a heat engine, and therefore it has to have a condenser that's colder, right? So say that you have something that's close to absolute zero, and you add energy to it, okay? You've added energy to it, but it's still colder. This region is still colder than anything else you can find. So how easy is it going to be to use that energy again? Basically impossible, you know? So basically you've just thrown that energy away. You're never going to see it again. It's still there as energy, but you can't use it to do anything useful, okay? So you would expect that to produce a big increase in entropy. And if you look at what this equation says, so say you added 500 joules of heat to something at 0.1 Kelvin, okay? You'd have an increase in entropy of 5,000 joules per Kelvin, okay? So that's a big increase in entropy. Whereas if you added 500 joules to something that's at 400 Kelvin, or say 1,000 Kelvin even, that's pretty hot, right? So it's not too hard to find a condenser that's cooler than that. It's not too hard to use that energy again to produce work. And so the increase in entropy there is not that big. It's only 0.5 there. Any questions about that intuitively?
So basically lower is better. Just think of lower entropy.
Yeah, you want lower entropy. It's more useful. And anytime you add energy, you're increasing the entropy in that system. The only question is, are you adding a little or a lot? Okay, if you only add a little, it's more likely that that energy will be recycled, you know?
So in the case of, steam engines then, so you're saying that energy is being recycled?
Well, no, the gas is being recycled because it's going around, but the energy, is, I mean, you could measure the entropy of the gas, in the, so you're adding energy to it at the boiler. And that's adding entropy. At the condenser, you are extracting energy from it. I don't know. There's not,
So it's not.
don't think about that.
All right, never mind.
I don't think there's anything there to, okay. So this is the mathematical definition of changes in entropy. So now I want to talk about what this is useful for, the second law of thermodynamics. So the second law of thermodynamics relates to entropy. And it says, in any process, this is like the most sort of science fiction-y law of physics. In any process, the total entropy of the system plus its surroundings in other words, the total entropy in the universe increases. So we have, you know, the universe has a lot of energy in it. And every single thing that happens is slowly making all that energy less useful. Okay? So little by little, if you think of like an instant after the Big Bang, okay, like quarter second after the Big Bang, all the energy in the universe was concentrated in one spot, not very big, you know? And everything else was basically absolute zero. And so you had almost zero entropy at that point, almost just perfect concentration of all the energy. Then as that energy has spread out and all these things have happened every time you start your car, every time you move, think, slowly energy that was useful a second ago is becoming less useful. And the final effect of all this is that at some time in the future, probably after the year 2020 sometime, all energy is going to be evenly spread out. Everything will be the same temperature and no mechanical, there'll be no motion anymore because no work can be done, you know? Eventually,
Then that entropy will just reverse as the universe collapses in on itself.
so, yeah, depending on what your opinion is of how the universe will meet its end.
It's supposed to die out and it's not supposed to come back into itself.
Yeah, I think people, it's still a little bit of a, that's still a little bit up in the air, I think. But this won't happen for a long time, so you don't have to worry about it. But it is kind of an interesting fact of this law that eventually, even though there's all this energy, it'll all be useless. An equivalent statement of the second law of thermodynamics, and this is kind of cool. Because at first thought, it doesn't seem like these would be equivalent. Statement of the second law of thermodynamics says in an isolated system, heat can only flow from a high temperature to a low temperature. Okay, so this one, you look at that and your reaction is, well, duh. So how are these equivalent? Question?
Shouldn't the second equivalent statement, shouldn't that just mean that it's not gonna stop then? Because eventually the low temp will be higher than the old high temp, and the energy will just flow back,
It'll flow back, yeah.
and then
Well,
it'll happen again. Or is it just like slow down as it goes?
it doesn't oscillate like that. Heat only, so you know what I'm,
Yeah, okay.
so it won't ever pass that point of them being the same temperature. It'll just reach, they're the same temperature, and then there's no more heat flow between them. So how are these two statements equivalent? Equivalent. Okay, so think of this example. So let's say that you have some amount of water over here and some amount of water over here. And let's say that this one is at 20 degrees Celsius and this one is at 80 degrees Celsius. Okay? And let's call this, the water over here, body 1, and the water over here, body 2. Okay? So the second statement of the second law of thermodynamics says heat is going to go from the 80 degree water to the 20 degree water, right? So Q is going to go this way. And let's just pick a number for an amount of heat. Let's say 100 joules of heat flows from 80 degrees to 20 degrees. So what happens, or what's delta S for each body? For body 1, so the temperature is equal to, we have to, I didn't mention this, I guess, but this temperature in the change in entropy equation, that's not a change in temperature, so that needs to be in Kelvin. So for body 1, the temperature is 273 plus 20, so 293. And so the change in entropy for body 1 is 100 joules divided by 293 Kelvin. Can someone divide that for me? Okay, joules per Kelvin. And now for body 2, the temperature is 273 plus 80. So we have 353. And so the change in entropy, and now we have to think about these signs, okay? I sort of glossed over it, I guess, here, but body 1 was adding this entropy, was adding this energy, this heat, and so that was positive. But over here, now the 80-degree water is losing 100 joules of energy. So this is negative 100 divided by 353. And what do you get for that? Can you divide that one? Negative 0.28 joules per Kelvin.
Could you repeat why is it negative one then? Why is it-
Yeah, because the Q in this equation is heat added to the system. So if we're looking at body 2, it's losing heat, so that has to be negative. And so add these two together, and you get that the total change in entropy is equal to positive 0.34 minus positive 0.28, and you get a value of 0.06 joules per Kelvin. Okay. So one of these bodies increased entropy, one of these bodies decreased entropy, but if you add up what happened to everything, you got a positive total entropy. And can you see mathematically why that has to happen if heat always flows from high temperature to low temperature? Because you're exchanging the same amount of heat. One's positive and one's negative, but the one that's positive has a smaller denominator. The one that's negative has a bigger denominator. And so the total entropy is always increasing. Yes. Yep, right. The high temperature is transferring heat to the low temperature. So this example is supposed to show how this statement that heat can only flow from high to low temperature gives the result of that first statement of the second law of thermodynamics, saying that total entropy always increases. Do you see that? Okay. Any questions about entropy or any of that stuff? And if you want to sort of have an intuitive thing to hang this on, it has to do with the fact that what the second law of thermodynamics says is any thermodynamic process, you're taking energy out of something at a high temperature and putting it into something at a low temperature. And putting energy at a low temperature makes that energy harder to access again in the future. Okay, let's do a problem or two. I don't have any problems. So let's go home. So I'll do some more I'll do some next time. So, but that's the end of the lessons on thermodynamics. So I'll go through some example problems next time. And then the next thing, we finally get into electricity and magnetism, which is kind of the heart of this semester. So, all right.